Hello again. This is video lecture 36.2, and we're going to be studying section 2 in chapter 36, in which we're going to figure out a way to calculate the intensity of the light that we observe on the viewing screen when we are seeing a single slit diffraction pattern. So let me remind you of the geometry, which we talked about in the previous video lecture for single slit diffraction, and then talk through how we're going to calculate the intensity. First, let me remind you that for any kind of wave, you can talk about the intensity of the wave, which is the power per unit area, okay, at any point in the single slit diffraction pattern. Power per unit area. So the SI unit would be watt per meter squared. And that's the intensity of the wave. Okay, the geometry is here, like we talked about already. First, we have a screen B with a long, narrow slit cut horizontally in it. And the width of the slit, which is the narrow part, is A. And the length is coming out of the screen, and it's longer than A, considerably longer. And we're sending in an incident plane wave perpendicularly on that screen. And the distance between these two adjacent plane waves, wavefronts, here, is the wavelength, lambda. And if it's visible light, that's going to be in nanometers. Okay. But we're assuming the slit width A is a little bit bigger than the wavelength, right? This picture shows that. Not smaller than the wavelength, a bit bigger. Not huge amount bigger, but a bit bigger. Basically as this picture shows. Okay, here's what we're going to do. We're going to imagine dividing the slit width A into capital N zones or regions, each of with delta X, which would then be A over capital N. And I'll just sketch roughly the center of what a zone in terms of what we're thinking about. So these dots represent the centers. I'm trying to space them out more or less equally of these capital N zones, where capital N is just some reasonably large number. Okay? And each of those zones acts like a source of a wavelet that's then going outward, a spherical wavelet, so it's curved wavefronts, that's going outward into the region to the right of screen B. And that's the representation of the flaring, the bending of the wavefront as it goes through the obstacle. And then what I've got those spherical wavefronts from the wavelets. They're spherical now because we're bending the wavefront. And we've got a bunch of them, capital N of them. So at point P on the viewing screen, we let those N wavelets interfere to see what kind of resultant wave we get. And do we get fully constructive interference? That would be a bright fringe. Fully destructive interference? That would be a dark fringe, or something in between. Now, the phase difference between wavelets from adjacent zones, so maybe these two, for example, at the point P, right? So there's a ray, and there's a ray, nearly parallel. The phase difference between those wavelets from adjacent zones is because they traveled slightly different distances to get to point P. So the phase difference, we'll call it delta phi, between those two wavelets is 2 pi over the wavelength times the path length difference for those two wavelets. And that would be the distance between the wavelets in the slit delta x times the sine of that angle theta that goes out to point P. That's the same way we did path length difference for two slit interference. So just think of those two wavelets as two sources, like two slits. Very, very small ones. Okay. Now, we assume that the wavelets that are arriving at point P all have the same amplitude. We'll call that delta E for the electric field part of the wave. And our job is to find the amplitude, we'll call that E sub theta, of the resultant wave at point P from adding up, superposing all the wavelets that come from all those little point sources that cover the whole area of the slit, all converging on point P. Okay, so we have to take all those wavelets and do a resultant to get the total. Okay, and that will give us what we're going to label E sub theta. I'm going to get rid of some of this stuff now. Where the theta, as you can see, as always, is the angle from the central axis out to point P. And the way we're going to get that resultant amplitude E theta is adding up the amplitudes delta E of the individual wavelets, but we're going to use, we're going to use a technique called adding phasors, which is a handy way to find the resultant of a bunch of waves. And phasors are in some sense kind of rotating vectors, but I'll show you how we're going to use it. Okay, now, what is this picture? This picture shows, going straight up and down here, right along here, the viewing screen. The viewing screen that was up here labeled C. Okay? That's the viewing screen. And we're looking at various points on that viewing screen, and we're asking what intensity of light, power per unit area, will there be at particular locations. And the first location we're going to pick is right on the central axis. So over to our left is the slit with the screen with the slit in it and the direction the light is coming from. And so that dotted line or dashed line I just drew is the central axis of the pattern. And so that point there on the viewing screen, I'll mark it with a red mark like that, is where the central maximum of the diffraction pattern will be. And I want to talk a little bit about how we use phasors to figure out what the resultant wave amplitude will be there. All right, so in this phasor approach, I'm going to expand this a little bit so that it's easier to see, I hope. You use a little arrow, like a vector, for each wavelet. And the angle between adjacent vectors represents the phase difference between the wave for those two vectors. Now, if we're at the central point on the viewing screen, where the central axis intersects, then we are right across from the very, very middle of the slit. And all the rays that came from the slit, remember the distance between the slit and the viewing screen is very large. They're all coming in from the same direction. They all travel the same distance. There is no phase difference between the amplitudes of the wavelets. So the little arrows, they're drawn here in this kind of orange arrow. Each one's in phase with the other. So they just draw the arrows all pointing in the same direction, each with a length delta E to represent the amplitude. And because they're all in phase, they all point in the same direction. And then you just use the rule for vector addition to get the resultant. You draw an arrow from the tail of the first to the tip of the last one. And that length is the amplitude of the net or resultant wave. And that's what this book is calling E theta. And this is the biggest amplitude we can possibly get when all those little phasors for the individual wavelets are all lined up exactly in the same direction. Okay? And so they call the amplitude in this case EM, M for maximum. Okay? Max. So we get the very largest amplitude of the resultant that we can get. We'll call it Emax. The intensity is going to be proportional to this amplitude squared. So it's going to be proportional to Emax squared. And so the intensity at that central maximum is the largest intensity we can get. It's even sketched here on this kind of sideways with a green, in the green color, in a curve. That's actually a plot, it's kind of hard to see, of the intensity versus theta. And the fact that we're at a peak here is telling us that it's the maximum intensity at the central maximum. Now we're going to consider a point slightly above, on the viewing screen, slightly above the central maximum. And we want to figure out, using phasors, what kind of resultant amplitude we're going to get. Okay? So here's what happens at a point slightly above the central maximum. Similar kind of picture, but now we're talking about this point on the viewing screen. So now, because we're not going right across the middle from the slit, wavelets from different zones of the end zones in the slit travel slightly different distances to get to this point on the viewing screen from adjacent zones. And so the phasors that represent the wavelets here at this point on the viewing screen from adjacent zones are slightly out of phase, so we're going to put a little angle between neighboring phasors. So let me show you with this blown up view. All right, there's one of the phasors, and then the phasor from the zone right next to it is tilted up at just a slight angle. And then here's the phasor from the zone next to it, tilted up at just a slightly larger angle. So each successive phasor has the same angle between it and its predecessor. And as you go down the zones, you're getting a cumulative effect. And so this chain of phasors, if you like, is curving upward because there's a little bit of an angle between each phasor and the one before it. And then to get the resultant, using the rule, treating those like vectors, I draw an arrow from the tail of the first to the tip of the last. And that length represents the amplitude E theta. At that angle, theta. That's why they call it E sub theta. It's the net amplitude at that angle theta. And I think it's pretty clear that this length here is smaller than this length down here. Okay? Because those phasors curve up a bit instead of going straight across. And so when you sum them, you don't get quite as long a vector as you did in the E max case. So this E theta is less than E max in this case. And the intensity of the light there will be proportional to the E theta squared. So the intensity will be less than the maximum. And so over here on this graph that represents the intensity at this point, go till you hit the graph, you don't go quite as far as you did when you were at the central maximum, meaning the intensity is a little bit less at this point. Okay? All right, now we're going to consider the point on the screen right here, which is at the first dark fringe, the center of it, the first point of destructive interference. What happens with the phasors there? Okay, so now here's what happens at the first dark fringe. Well, it's actually quite amazing. Now we've gone a little bit farther from the central axis, so the angle theta is a little bit bigger. And the phase difference between adjacent phasors is a little bit bigger. Okay, so now let me zoom in. So now we draw the arrows such that the angle of each phasor between the one before it is larger than it was before. And so you're really getting a lot of curvature of this chain of phasors. In fact, the curvature of each successive phasor is just the right amount that when you add up all n of them, all the way around, you end up exactly back where you started. So guess what the resultant of that is? 0. There is no net amplitude there. And so there is no intensity there. But sure enough, the intensity graph is 0 right there. And you have your first dark fringe. Okay? All right, let's go up to one more point. Let's go up to the point on the viewing screen that's at the first side maximum, which is where the next peak is up there. Although notice the height of that peak on the intensity graph is a lot less than the height of the central maximum. Still, we'll call this point right here the location of the first side maximum. Let's see what's happening with the phasors there. The first side maximum. I'll expand here so you can see it. Now, I'm at a larger angle theta from the central axis, and so adjacent phasors have an even larger phase difference between them. Okay? So this successive chain of the n phasors really coils around. In fact, it coils around, I'm going to draw it as a continuous curve, so tightly that it does a complete circle and goes a little bit farther before all n of them are done. And then the resultant goes from the tail of the first to the tip of the last, like that. And the length of that arrow is the E theta. And it turns out that as you're winding this chain of phasors up, so to speak, you're at a point where that blue arrow is about as long as you're going to get. And if you do more winding up, that blue arrow is going to get shorter. That's how you end up getting another peak. However, it's not a very big peak. Not certainly compared to the E max we had before, right? It only goes to here. But it is a side maximum, and it would show up as a somewhat brightish side fringe. Okay? All right, so you can do that kind of winding up of the phasors to understand why at certain locations on the viewing screen you'll see bright or dark or something in between. Let me show you with a Wiley Plus animation the same thing in action. Okay, so here we have a side view of the screen with the slit. Then we go across a distance big D to a viewing screen, which you can't really see because we're in the dark. But you can see on the viewing screen the bright central maximum directly across from the center of the slit. You can see the diffraction of the wavefront as it goes through, the bending. And then you see a whole bunch of phasors, all lined up exactly in the same direction to get an E net. In this case, imagines breaking up the slit width into 12 zones, so there are 12 phasors. And that's the maximum E net you can get. And so you have maximum intensity, and you even have a plot of intensity, and our red dot shows us where we are, and we're at a maximum. Now we can imagine we have a detector that can move along the viewing screen upwards. And right now, we're at a distance 0 from the central axis. We're at the middle of the central maximum. I'm now going to move that detector upward along the viewing screen away from the central axis. As I do, I'm moving to a slightly higher point on the viewing screen, and then the adjacent phasors from adjacent zones get a slightly different phase difference between them, and the chain of phasors starts to curl. And then the net phasor goes from the tail of the first to the tip of the last, and it tells you how big that is. E net over E1, E1 is the length of any one phasor, is less than the 12 that it was at maximum, central maximum. And if I go higher up, we get even more curvature. And the E net's getting smaller and smaller and smaller, so the intensity is getting less and less and less. And if I keep going with enough curvature, this chain will wrap around pretty much entirely on itself. And although I can't quite get to it, you could see how if I was very careful, I'd be able to get to the point where the chain really does wrap entirely on itself, and the net of that would be 0, and we'd be at the center of the first dark fringe. But we can keep going, and this chain just keeps wrapping up more, and there's that E net showing up. And we're right about now at the center of the first side maximum. And if I keep going, the E net's getting less again. And pretty soon, I'm going to be at the second minimum. I just passed it. Okay? So that's what's happening with the phasors as you imagine moving up the viewing screen. They're wrapping up into an ever tighter and tighter chain. Okay. So now there's one more thing I want to do. I want to work out a formula for the intensity. I is the symbol we will use. We use that in chapter 35. The intensity of the light in the diffraction pattern at angle theta it would be in the units of watt per meter squared. And the way I'm going to do this, and I'm not going to ask you to repeat this derivation, I just want to show it to you so that you can see that it's mostly geometry with the phasor picture. Let me show you. All right, now here's a picture showing the phasors in some kind of arbitrary intermediate configuration when successive phasors have a little bit of a phase shift between them, and we get this curved chain of them. All right, and then we take an arrow from the tail of the first to the tip of the last, and that's the resultant. And I want that length, E theta, of that blue arrow. I'm going to assume that there are so many of those phasors that curvature is actually smooth, and so it's really an arc of a circle. Okay, so here's what we want to do. We want to find that length, E theta. We're going to think of the phasors as forming an arc of a circle. And that circle has some radius that the picture shows, because every arc of a circle has some radius. We're going to denote R, okay, to its center of curvature. The length of each phasor, the length of the entire arc, I beg your pardon, is E max. In other words, if I took that red arc and I laid it out flat, it would be this long. The same thing as I got when they were all in the same direction, and that's E max. So that's the length of the arc in red. And then the angle subtended by the two radii up here, phi, turns out also to be shown down here. And it is the angle between the direction of the first phasor, which is to our right, and the direction of the last phasor, which is upward like so. Turns out those phi's are the same. That's geometry. So phi equals the total phase difference between the first and the last phasor. Or phasors, I guess I should say. That's what the phi is. Then we have put in a bisector there, going right down the middle, right there, of that angle. And so the angle alpha, just because we've bisected it, is phi over 2. That's just geometry. And another bit of geometry. The arc length, that's the red arc, that's EM, is equal to the radius times the angle subtended, which is phi. Okay? If phi is in radians, remember. And since phi is equal to 2 alpha, I'm going to write that as R times 2 alpha. All right, now look at this right triangle formed here between these three sides. Or the other right triangle, doesn't matter. Yep, that's a right angle right there, yes? So just from right triangle trigonometry, let's figure out the sign, an expression, for the sine of alpha. See the alpha up here? Sine is then opposite over hypotenuse. Opposite length is E theta over 2, half of E theta. Hypotenuse is the radius. This is E theta over 2r. But from this expression right here, 2r, beg your pardon, is equal to E max over alpha. let me substitute that right there. So this is E theta over E max over alpha. That puts the alpha up there. And now we solve for E theta. So E theta is E max times the sine of alpha over alpha. Now remember, intensity at angle theta, I'm going to get an expression for the intensity at angle theta divided by the maximum intensity will be given by the resultant amplitude at angle theta, E theta, over the maximum amplitude, E max, squared. The intensity goes like the amplitude of the net wave squared. And so that goes like sine alpha over alpha squared, where alpha is this angle up here, which is half of phi. But phi is the total phase difference, right? Between the bottom of the slit and the top of the slit. And then we know how to write that. That's got to be 2 pi over the wavelength times the total path length difference between the top of the slit and the bottom of the slit, which is the slit width A times sine theta. So if that's phi, then alpha, which is phi over 2, is pi A sine theta over lambda. And that's what we use for alpha, and that goes there and inside that sine. Okay, alpha is an angle in radians. And this is what we are going to do practice with in class on Monday, using this intensity formula. Pick a point on the viewing screen, usually call it point P. You got to know what angle that point, the line of that point P makes with the central axis. That's the theta. I need to know the slit width, A, the wavelength of the light coming in, lambda. And then I can use this formula to calculate the intensity you're going to have, at least relative to the maximum intensity. And that's generally what you mostly care about. So that's what we're going to be practicing with. Before we do that on Monday, here's a class engagement exercise for Blackboard. It goes like this: single slit intensity for single slit diffraction pattern. We're going to use 2 wavelengths of light, 650 nanometers, which is in the red region of the visible spectrum, and 430 nanometers, which is in the violet region. They're used, at least initially, separately, one after the other, in a single slit diffraction experiment. The figure here shows the results as a graph of intensity I versus angle theta for the 2 diffraction patterns. So there's one curve there that's a continuous curve, and the other one is a dotted curve. They both plot I, intensity versus angle theta, on the viewing screen. Now suppose we use both wavelengths at the same time. We shine them both on the same slit at the same time. What color will be seen in the combined diffraction pattern at the following angles on the viewing screen? This point, that's called angle A, and that point, angle B. What color light will be observed at point A on the viewing screen and at point B? That's what you answer for the class engagement. So as I said, we'll be practicing with this intensity formula in Monday's class, and that's all for this video.